Hello students, the question is, there is a uniform spherically symmetric surface charge density at a distance r0 from the origin. The charge distribution is initially at rest and starts expanding because of mutual repulsion. The figure that represents the speed v of the distribution as a function of its instantaneous radius r is. The options are given. This question is taken from JEE Mains 2019, 12 January, first half. Okay, read the question again. There is a uniform spherical symmetric surface charge density. So uniform surface charge density at a distance r0 from the origin. See, so the diagram, suppose this is the origin and this is the spherical charge distribution. It has an initial radius of r0. So it's a spherical charge distribution, mind it, and it starts expanding. Suppose the charges are positive and it starts expanding due to their mutual repulsion. Initially, the initial velocity is given as 0. See, the charge distribution is initially at rest and starts expanding because of mutual repulsion. So the initial radius is r0 and initial velocity is 0. In the first step, we have to find the self potential energy of a spherical shell. What is the formula for self potential energy? First of all, we have to understand what is the self electric potential energy actually mean. Suppose the charge at any instant of time on a spherical shell is q. Suppose charge at any instant of time is q. So q charge is given and the charge gets uniformly distributed and the radius is r. Okay, now what is the potential on the sphere? The potential on the sphere is very easy. V equals to 1 over 4 pi epsilon naught, that is k, into q divided by the radius, right? Now a small elemental charge, suppose dq, is brought from infinite to this surface. Suppose I brought a dq charge from infinity to this surface, infinity to this surface. The work done will be work done to bring dq from infinity to the sphere. What is the work done? So work done will be potential into dq, that is kq dq divided by r. Therefore total work done, suppose initially there is no charge in the sphere and the charge is increased from 0 to a final value, suppose capital Q. So total work done is nothing but integration of this. Suppose initial charge is 0 and final charge is Q. So it's a very easy integration. K by R is constant. Integration Q dq from 0 to Q, which will give you K Q square by 2R. Therefore this is the formula for self potential energy of a spherical shell, right? Okay, let's go to the next slide. So initially the radius of the sphere is r0, right? And suppose the charge is q. So initial kinetic energy is 0, right? Because the sphere starts expanding from rest. Initial potential energy is K into Q square by 2R naught, right? And due to their mutual repulsion, suppose the radius has changed to R, but mind it, the charge, the amount of charge it contains, it doesn't change, right? Still remains at Q. So suppose the velocity now becomes V. So final kinetic energy is what? Half mv square. You can see in the question they ask you basically the speed of the distribution, right? So the speed, suppose the speed is V, and final potential energy is k q square. Q is has not changed, so q square by 2 into R, right? Therefore, from the principle of conservation of energy, I can say that the initial kinetic energy plus k q square divided by 2R naught is same as half mv square plus k q square by 2R. Okay, therefore half mv square is nothing but k q square by 2 common, 1 by R naught minus 1 by R. All this thing, see, half m, k q square by 2, these are constants, so I can write that v square is equal to, so therefore v square is equal to some constant, suppose k, 1 by R naught minus 1 by R. Right, student? Right, student? 1 by R naught minus 1 by R. Therefore I can say v square is proportional to this. Now we want to find the nature of the plot. See, this is not a very simple plot. Here R is plotted along x-axis and V is plotted along y-axis. I will analyze this equation in a different way. Suppose when R equals to 0, put R equals to 0 here. If R equals to 0, then what will happen? And if you see, look at the options, these options. See, this point is basically R naught. Okay, this point is basically R naught. This is not 0. This point is basically R naught. Therefore, I can say when R is not 0 but R is equal to R naught, then V is equal to 0. Therefore, definitely I can say that the plot starts from this point. Okay. Now when R tends to infinity, if R tends to infinity, we can say 1 by R tends to 0. Therefore V square is equal to k by R naught, which is a constant value. Therefore I can say that when R increases from 0 to infinity, or R naught to infinity, not 0, initial value of R is R naught, so R increases from R naught to infinity, then this value of V saturates, right? Therefore I can say that the plot will look like this. When R becomes very high, the value of V tends to root over of k by R naught. So this coordinate is root over of k by R naught. This coordinate is R naught. Okay. And if you look at the other options, see, so option 1 is correct first of all. And if you look at the other options, see, in this option, if R is increasing, V is not saturating, but if V is increasing, R is getting saturated, so this is wrong. In this, you can say the slope is changing. Here also the slope is changing. Now how do I understand? Look at option 1 and option 4. The two options are almost same, but how do I understand the nature of this plot here and the nature of this plot here? For that you need to do derivative to find the slope. So v square equals to k 1 by r naught minus 1 by r, and if you take derivative of this with respect to r, suppose, so it will become 2v into dv by dr. This thing will be, so 1 by r square, right student, because derivative of 1 by r is minus 1 by r square, so minus minus becomes plus, so k by r square, right? Therefore the slope of this plot dv dr will be k by 2v r square. Now see, if r increases, this value will decrease, and if r increases, this value decreases, therefore v should also increase. Therefore I can say the slope, this is the slope na, so with increase in r, slope is decreasing, right? And this decrease is continuous. Therefore I can say definitely option 1 is the correct answer. Thank you for watching this video. Please subscribe my channel Phi Solver.